So thank you very much. Thanks to the organizer, David, Igor, and Christophe. I'm very happy to be here. So as Peter said, the Chebyshev density theorem, it allows you to count primes congruent to A mod L because you can see it as a conjugacy class in a certain Galois group. And the certain Galois group was associated to the cyclotomic field. So I want to develop the same tool for elliptic curve and then do a lot of application of that. Distribution question related to elliptic curve. So let's start by E is going to be an elliptic curve over Q. So it can be given by an affine equation like that. And you actually can take A and B to be integer. And what's EQ then? EQ is just the set of points. So define over Q means A, B are defined over Q, but then I can take them in Z. EQ is just going to be the set of solution to that. So this is the affine, okay? If you know about the elliptic curve, this is the affine part of the curve. There's also a part at infinity that I didn't write here. So this is the set of solution, well, x, y are in Q. Well, it's a weird way to write that. Union, the solution which are, so to say, at infinity, which is to say, here this is the affine part where z is 1. I can put z equal to 0, and in fact, if I put z equal to 0, there's only 1 point. Only 1 point at infinity. So if you look at that, E over Q, of course it's an abelian group. It's also a finitely generated abelian group. So it writes as an infinite part plus a torsion part. Okay? Because it's a finitely generated abelian group. Okay, this is due to Mordell, and over number field in general is due to Weil also. So, and if you look at that EQ torsion, okay, it's a simple group of, well, it's a simple group. Not many things can happen for the torsion over Q. This is proof. This is a big result to show that. That's Mazur's theorem. We classify all group which can occur as torsion group over Q. So one of the things that I want to look at, and Peter talked a bit about that, is not to be confused with EQ torsion, but EL. So people always write EL, and what is meant by that, when you don't put the field, is that there's an enormous field. It's over the algebraic closure. So EQ torsion is very small, but EL has a very regular structure. So EL is the set of P in EQ bar such that LP is equal to 0. Okay. So I have an abelian group, so the abelian group I write additively, so by LP I mean adding P to itself L time. Okay? And by P I just mean a point on the curve. So what's happening with EL? Well, there are several ways to know about the structure of EL. What you can do is you can do it explicitly. So adding point on a curve, if you ever saw this picture, is made by, taking a line intersecting the curve and finding its intersection point. So you can write equation for that, okay? So it's tedious, but you can write equation for multiplication by n. Okay, so L is always, for me, going to be a prime. But those formula I can write in general for multiplication by n is if I can take n times a point, I could write formula for what is n times a point. So let me write it like that. Okay, so the denominator is a certain polynomial. My point P is xy. So the denominator is a certain function of P, and the numerator, I think the standard notation is phi n omega n. It doesn't matter that much. So one can write explicit equation for the multiplication by P, and if you write those explicit equation, if you look at the degree, well, because there's a square, there's a degree. This depends on x and y. Of course, y squared is x cubed plus ax plus b, so maybe you can write it only as a function of x, maybe at the you have to take a square root, but because here it's a square thing, you have a degree only in x. So if I write degree in x, maybe I can write it like that, or I can still. So as a polynomial in x, this has degree n squared minus 1, which you can write explicitly. So if you can also show that all the roots are distinct, it's going to give you the number of points of order n, of exact order n. And what do you get? Then from that, it's not hard to conclude then. No, because it's degree of the square. The degree of the square, yeah. Okay. Oh, why, by the way, I'm interested in knowing that? Because I want to know the ℓ-torsion. Okay. This is where you have to think of an elliptic curve as something projective. What are the points of order n? Those are the points which are sent to the point at infinity. And the point at infinity are when the z component is 0, which is to say when there's a division by 0. So if I want to know about the ℓ-torsion point, they would be the roots of the denominator, because you were looking at a projective curve. So you add points, and sometimes you would get something where there's a division by 0, where in projective coordinate, division by 0 are not bad. It just means that we move at infinity. So because this polynomial square has degree n square minus 1, there's also the point at infinity, which is not counted there. If I can show that this polynomial doesn't have double root, but everything is completely concrete, I get that the number of ℓ-torsion point is n squared. Okay? Which implies, okay, because this is true for every n, this implies that the structure of En because it's true for every n, so it cannot be a full cyclic group of order n squared, because then there would not be enough ℓ-torsion point for every n. So this is not the torsion again over Q, but just the general torsion. So this is something we will use. And let me, because I'm there and I have the ℓ-torsion map, let me recall about CM curves. Okay. So this was said by Drew. So by this multiplication by n map, we have, of course, that if I look at the endomorphism of my curve, well, Z is contained in that, of course. It's an abelian group. So, and Z is contained in that by saying, well, every n corresponds to multiplication by n map. And in general, okay, this is the full endomorphism ring. If not, ESCM. And those CM curves have different properties than the other curves, so most of the time I would exclude them. So most of the time I would exclude CM curve. So let E be an elliptic curve over Q without CM. And what I want to do is I want to look at properties of the reduction, exactly like Drew was telling one of them, maybe the most famous one, which is the Sato-Tate conjecture. You fix a global curve, and at every prime p, you look at the normalized trace, and you look at the distribution of the normalized trace. But there are several questions you can state like that. So look at EP for all prime, well, all primes are all prime up to x, if you want to state that in some analytic context, and look at properties. Well, maybe I should say look at properties of the reductions. Of the reduction. AP, well, for P, let's say for all primes. But if I want to state them as an asymptotic thing, of course, I would have to say prime up to x. So what do we mean by that? I have to talk a bit about elliptic curve over FP. Okay. So first of all, of course, I need that P does not divide the discriminant of the curve. Tori Q plus 27. And maybe I should take the curve to have minimal discriminant. So when I say P does not divide the discriminant, it really means that the curve has bad reduction, or to say P does not divide the conductor. So now let's start with an elliptic curve over FP. So maybe okay. So what we want to do is take a global curve and look at all reduction. But now let's just start over FP. So let's start with a curve E over FP. So as we saw, E over FP, well, an elliptic curve over a finite field, it's again an abelian group. And this, I think, Igor is going to talk about that. It's an abelian group of rank at most 2. Okay? Because we just saw that the point of order L have this structure. So here what happens is because you have a finite group, it has this structure. And I think Igor is going to talk about that, about what possible group can occur. So that's one thing we know. We also know that, of course, the number of elements of E over FP, well, I can say it's smaller than P squared plus 1. It's finite, certainly. And let's say I want to know about the number of elements. Maybe I can write it like that. The number of elements, well, there's the point at infinity. And what is the number of elements? Well, you have your equation, which is x cubed plus ax plus b. Every time I put a point in fp there, I'm going to get, every time I put a point in fp as the x, I'm going to get a point on the curve if and only if it is a square. So I can write the number of points like that. Okay, so if I get a 1 plus, yes, sorry. When it's a square, I get 2 points. When it's not a square, I get 0 point. And with 0, I get 1 point. Okay? So 1 plus 1, when this is a square, I get 2. When this is a non-square, I get 0. And when this is 0, I get 1. That's okay. So, and then I get my p plus 1 plus the summation. Okay, and now let me write it like that. And that's one of the reasons we can think that this AP is small, because it's a character sum, and this character sum should oscillate. Okay? X cubed plus AX plus B, it's not going to systematically take squares or non-square. It's going to take, well, half of the time square, half of the time non-square. But this is something actually that, you know, you think the best proof for that will be, okay, deal with the character sum where analytic number theories and see how it oscillates. But actually the best proof for those kind of things are actually algebraic proof. So how can we, let me just say a few words about, so, and then was the theorem of assay, is that the number of points of E over Fp minus P plus 1, well, this is smaller than 2 square root of P. Which, you know, from that point of view, it makes sense. This thing should not be too big. And how we'd prove that, and the reason I want to say a few words about this Blackboard management is not that easy, now I realize. Yeah, I know, but to go up is okay, but to move down, don't worry, I won't climb, and I will use the switch. Okay, so how would you prove that? Well, there's a very important thing, which for me I'm going to denote phi p, but, well, Peter denoted Frob p. He denoted Frob p over q. But this thing also exists for elliptic curve. Huh? It's the things that sends xy to x to the p, y to the p. Okay. So this very important map, because my curve is defined over fp. Of course, over q it doesn't work. It's not an endomorphism of the curve. So there's this very important map, and the number of points of E over Fp, okay? In general, when you work over Fp, everything is given by the Frobenius. Now that's your main tool. You want to hit everything around with the Frobenius. And, well, for example, you can know the number of elements, because that's, of course, the kernel of 1 minus the Frobenius. Okay, that's the definition of the point over Fp. They're invariant by the Frobenius. And how to understand that? Well, when you look at map of curves, so I have the Frobenius, but I can have any map. The way to understand that map of curves is to understand that as field injection. Okay, that's the best way. This is the duality between curves over finite field and function field extension. So when I look at this map of curves, a good way to understand it would look at, I have a map from, well, here it's going to be Fp. The function field of my curve to the function field of my curve, which is to say, everything that is a function that I can write on the point of my curve, this is the function field of my curve. And what's this map? This is this natural map. Okay. So this gives me a field extension. This gives me that if I have the function field of my curve, I can see it as, so this, let me call that. And by the way, this is an injection because those are fields. So Fp of E, that's the function field of my curve. What does it mean? It's just Fp of xy quotient by the ideal of my curve. So it gives you function that lives on your curve. So think about map between curve. A very good way to think about that is about field extension. And then what you call the degree of the map is the degree of this extension. This I would call, this degree of this extension, I would call the degree of my map. So the number of elements in the kernel, that's going to be the same thing as the degree of this extension. So maybe I call it the degree of phi. By that I mean this degree. Well, not exactly, huh? Because here, and that's very important, that's the difference between supersingular and ordinary. Things are not necessarily separable. It's going to be the separable degree. And here what's going to happen is that, okay, this is something which is true. This is not a one-liner. But 1 minus the Frobenius is separable. Okay, because basically P does not divide 1. okay, which is not a thing which is easy, but this is true. So the number of element of that is going to be the degree of my map. And now this map, it's in a way an abstract way just to build those polynomials. Okay? And this map would have degree, so well, I was to say, in the case of multiplication by p map, I would know that degree. Here, I don't know that degree. Okay? So the number of element of the kernel is the degree of that map, but the degree which goes from the set of endomorphism of E to Z, it's a positive definite quadratic form. So what does it mean? It means that if I do, okay, let me just do it like that for now. So if I do the degree of 1 minus the Frobenius minus the degree of 1 minus the degree of the Frobenius, this is going to be smaller than 2 times square root of the degree of 1 times the degree of the Frobenius. I'm sorry. Yeah, the map is not phi. Yeah, sorry. I was doing it for, so phi is 1 minus phi p, exactly. Yeah. I don't know who said that. That's, yeah. I was writing that for a general map, but here, of course, I would mean. Good thing I didn't use phi for 2 different things, so it's still going to work. Yeah, thank you. Okay, because I went to define the degree for a general map. Okay, so from that you would mean, well, what is that? Well, by this observation that this is my degree of phi. This is the number of element on the curve. This is 1. This is the degree of the Frobenius I know. The degree of 1 minus the Frobenius, I don't know. I'm approximating that. It gives me the number of points. But the degree of the Frobenius, I know it's p. So the number of points minus 1 minus p is smaller than 2 square root of p. Okay, that's the proof I see. So I mentioned that because I'm going to use those tools. But of course, another proof, would be to say that, well, frob p or phi p satisfies okay. Or AP is this number I'm looking for, the difference between the number of point and p plus 1. And the roots, so satisfies that. What do I mean? When you look at this action on the Tate module. Okay? And when you go for, on the Tate module, which means there's no congruence model, it will satisfy this polynomial. And this polynomial has 2 roots, which are Weyl number. And the Weyl number of psi square root of p. So the trace is bounded by 2 square root of p. Okay, so that's about the elliptic curve over Fp. The first 2 things I mentioned is that, well, it has a certain structure as a group because you're over Fp. It has a certain number of points. And another thing I could mention is also that something we notice is that elliptic curves over Fp always have Cm. Because I just showed you that it has more multiplication than just multiplication by the integer because there is the Frobenius. Okay. Elliptic curves over Fp always have Cm because you have the Frobenius. And this is going to be, so let me say something and explain. And now, so this is Z adjoint the Frobenius. By the way, Z adjoint the Frobenius, this is simply Z adjoint square root of AP squared minus 4p. Huh? This is the Frobenius satisfies that. So Z adjoint the Frobenius, which is that. This may or may not be the full ring of endomorphism. And I'm going to write something as here. I'm going to write them. Let me write K is Q. Okay, and let me write OK as the maximal ideal. So what I want to write here is maximal order. Yeah. Sorry. Thanks. Let me write. Okay, so here, if the curve is super singular, this is not going to happen. So I can either say, okay, I'm looking at the portion which is only in that ring. Okay, I'm forgetting about the portion which is outside that ring. Or I can fix it by putting that, but I don't like that very much. But or I can say my curve is not super singular or something like that. But why do I want to say that? Because there's something which is nice, which is the AP, but there's also something which is an important invariant, which is the BP, which is the index. which is the index of the was generated by the Frobenius inside the endomorphism ring. This index is easy to compute because this index is just about AP squared minus 4P, remove all the squares which are in it. You know what's the maximal order. But here, you know, the BP is not necessarily the full square number. It's not necessarily the number that would make AP squared minus 4P squared free. Okay? This is more mysterious. Okay, so I'm defining all them because the question I'm going to ask, I'm going to be related to those. And finally, let me state this thing that I said to you, is that elliptic curve over FP fall in two categories. Maybe one way to say that, if I look at that, I have my elliptic curve over FP, so I can look at that. Huh? What's the ℓ-torsion point? And again, I put FP bar so that you remember that this is usually called EL. But let me put the FP bar. So this is again, well, of course, I have to put some condition here. But now what about the P torsion? What about the P torsion of elliptic curve over FP? So it smells like something would be weird here, or something would at least be different. And it is true. And there are two cases. So let me write it like that. It could be Z over PZ, or it could be 0. Okay? It never has rank 2. It either has rank 1 or rank 0. And when is going to be that? Well, this is going to be that if and only if the multiplication by P is purely inseparable. Okay? I'm writing that because, of course, that's what you know, if the multiplication by P is purely inseparable, there's no root. I mean, there's just one root. So this is this case. And this would be if the multiplication by P is not purely inseparable. Okay. The multiplication by P is the Frobenius times the dual of the Frobenius. The Frobenius is always purely inseparable, but the dual may or may not be. So there's this case. I can also say in this case, this is the case where the endomorphism ring of E, which is always a curve over FP, is an order in a quadratic imaginary field. And this order, well, you know exactly which quadratic imaginary field because you know this contains that ring. And here it's going to be, it's an order in a quaternion algebra. So here we can also say this is if and only if AP or AP of E is equal to, not equal to 0, sorry. So yeah, but now I'm dealing only with curves over FP. Yeah, now I'm over FP, my curves over FP. I don't want to say the reduced curve I call EP. And now I'm saying, let's forget about the global curve, let's just go over FP. But you're right, this is an elliptic curve over FP. The endomorphism defined over the algebraic closure. Yeah, all the way. Well, in that case, it will make no difference, huh? Yeah. That is what's kind of what I was fiddling about here. Okay, so, and this is the thing, so AP is not 0, this is AP is 0. And this is called ordinary. And this is called supersingular. And Peter mentioned that one of all the conjecture I'm going to say, there's only one case where you can show infinitely many, and it's going to be because of supersingular, because there's this extra structure which allows you to do something. Okay, I think that's what I wanted to. With those properties, I can define the question that I want to study. So, and I want to write them on the. Yeah, I think I'll take a big board so then I can use the whole. I can write the conjecture and the results all on one line. I need a big line. So what are the things that I wanted to mention? So I want to look at various conjectures such that now, okay, this was about the elliptic curve or FP. Now I'm moving back to I have a global elliptic curve and I look at all reductions at the same time. So for example, I could ask about the number of p smaller than x. I'm never going to write, but always p is a prime of good reduction. Okay, if p divides the conductor or the discriminant of the curve, I don't count that, such that, for example, AP of E is equal to a fixed value. That's going to be one type of question I could ask. So what's the density of the set of prime? They will all have zero density, but can I say, so can I determine the density in terms of, even if it has zero density? Can I say there are infinitely many? Can I have non-trivial upper bound and things like that? So I could also look at the number of primes smaller than, well, maybe I could have said that the first one I should have mentioned is the one that Drew mentioned. I'm not going to talk at all about that, about the sadotate, which would be the number of, when you look at the number of primes smaller than x, or maybe I'll write it, such that the normalized trace, I think when you normalize, you keep it between -2 and 2, or? Okay. So belong to some interval alpha beta, which is contained then into -2 and 2. Okay. Which is the one I'm not going to talk about because we'll have 6 hours of lecture on that. And it's given by this very cute measure. You integrate between alpha and beta, this sadotate measure. My curve is a non-CM curve. So then it would be the sadotate. Okay, this is another question, and you would think, come on, if I know the normalized value of AP, this was proven. Suddenly I know AP is equal to T, but of course not. You divide by square root of P. You're doing a lot of change from a point of view of measuring things. So even if this one is completely solved, this one is not at all completely solved. So here I'm not normalizing, I fix the value. For example, when is AP equal to 0? How many supersingular reduction we have? So I could also say, I told you, well, to be equal to 0, so supersingular or ordinary, there's this ring which characterizes thing. So I could fix a global ring or a global field and ask when is, the endomorphism ring. So maybe I could write it as the endomorphism ring of the reduced curve tensor with Q, because I want the field is equal to K. So here, T is fixed. Here, of course, alpha, beta are fixed for the sadotate. So here, K is fixed. So those are things that people look at. There's also another quantity which can be interesting, which is how many primes smaller than x such that the group that you get when you reduce has a prime number of element. So this I can write as, well, this thing is p plus 1 minus AP. So I could say p plus 1 minus AP is prime, and I guess that's why people call it an analog of the twin prime conjecture, because p plus 1 minus AP looks like p plus 2. But in fact, if you write it like that, it looks more like something like counting Sophie Germain prime, if you compare with the number of element in the multiplicative group. So people who do cryptography, for example, have an interest of this group being cyclic, and as I said, I erase it. This group is not cyclic. It has in general rank 2. So prime number of element, of course, will give you cyclicity. So what are the things I can look at? So number of p smaller than x. So there's a new conjecture which is around recently, which is about p plus 1 minus AP. This is called amicable prime. P plus 1 minus AP is prime. And at the same time, q plus 1 minus AQ is p. So if I give a name to those, so this of course is called, so this would be the sadotate conjecture, the first one. Okay, so the second one will be the Line-Trotter conjecture. And if let me write it, I'm going to continue down and on the side. If I call that PET of x, so the conjecture is going to be that this is a certain constant. So PET will be, it should be on the first line. Okay. So the sadotate conjecture for a fixed trace would be that the number of primes such that the value of AP is a fixed value, this should be like that. Okay. So it has density 0. So for the second sadotate conjecture, this is also due to Line-Trotter. And also, it should be. So in all those conjectures, this is not difficult to guess. I mean, they're all very difficult to prove. There's almost no result above them. But this, the asymptotic is not difficult to guess. The constant, and this is one of the very nice features, can be written exactly in terms of property of the curve. And Nathan is going to talk a lot about that. So there's a very explicit constant. And, you know, Peter also discussed that. It's like in the Artin conjecture. This constant you can understand in terms of probability, which you believe to be independent. And this is what you write. It's always right as an Euler product. But, you know, this is only a heuristic. So trying to prove anything about this constant is difficult. So this one is due to Koblitz. So PE. So maybe I call it twin. So it should be a certain constant depending on E. And x over log square x. Okay, it's like the twin prime conjecture. So x over log square x, the number of twin prime. So this one is a new, so I'm saying that because this was due to Silverman. Okay, when I say the Koblitz conjecture, maybe if I want to put the name of the people who did the conjecture, when Koblitz first made the conjecture, his conjectural constant was wrong. So this was refined by David Zewina. So this one was first mentioned by Silverman and Stange, and actually they kind of made an imprecise conjecture, but the really precise conjecture was done by Nathan. I don't know, maybe I call it amicable. And there's a certain constant. And this one, I guess, would be like that, huh? If I do my density correctly. So I'm presenting a lot of questions, so they will have the feature that, okay, I will try to use the Chebudarev to do things on those, but already what I'm going to present for those two, I'm going to study this one and this one. I'm also going to do some sieving for this one. Already here, the technique do not work. And why the technique do not work here is like, in this one, we will need a Chebudarev at PQ. We have 2' P and Q, so we kind of need a Frobenius at PQ, when such a thing does not exist. So maybe that's an interesting question for people to think about. You'll see I'll discuss more about that. This question, and maybe I wanted to say that other plus. So two things where really not much is known. So I'll present that maybe as open problem, and if people are interested in the Paris workshop to compute evidence for that. So what is called champion prime. So this is a mix between the Langtrotter, but it really belongs to the realm of Sato-Tate conjecture. So maybe I should write, you know, if I look at the maximal value of AP, I'll get the minimal number of points, which, so maybe I can look at the, well, plus or minus, which one do you want? The maximal number of, the number of points is P plus 1 minus AP. So how many times do you get that this is the maximal value it can be? So this really belongs more like the Sato-Tate. In fact, using the Sato-Tate, you can make conjecture for that. And another one I would like to say, it's a mix between the Koblitz conjecture and in a way things which are like the Artin conjecture. So the number of prime smaller than x such that the order of P at a given, so I'm fixing a global point is prime. Okay. So, and this one also, so an R belongs to EQ. Well, it's a fixed global point, not torsion. Of course, if the order of the group is prime, the order of the point is going to be prime, but one does not imply the other. And the reason I'm mentioning that, again, it's all in relation with the Chebudarev density theorem. There are things you can do here using sieving which are very nice. You would like to do it here, and there is actually a very nice, you know, the building tool of doing that is some Chebudarev density theorem to count things, but this comes without an error term. It just comes with a density. And as Peter said, maybe some people can be happy with a theorem without an error term, but as analytic number theorists, we're not happy. So you know what the answer should be, but there's no way to do any sieving or anything because there's no error term. So that's also very interesting. So those are more, you know, I mean, everything is open, but those are more speculative and open questions, and we'll talk more about them. Okay, so what are the results known on those questions? Well, in terms of lower bound, nothing except Elke's results. Nothing except Elke's lower bound. So pi e0 of x. So for infinitely many supersingular prime. I feel like Darth Vader here. Sorry, you're like. Maybe we should have a. Maybe it would be more comfortable to have the big helmet, actually. Okay. So, and what's Elke's result? The number of supersingular prime. As Peter said, that's a very, very nice proof because it's like Euclid's proof. You're saying, okay, let's say I have n supersingular prime, and you use those n to build the next one. And as Euclid's proof, it's super non-efficient. You know, to build the next one, you kind of multiply all them together and take it very, very far. So if you put that, actually you get exactly the same lower bound than Euclid's original proof. You get that, so which is far from the truth, but you get infinitely many. So what else you can do? So there's something that I'm not going to mention, but you can do average result. I'm not going to mention much. So what does it mean by average result? You can take, okay, so when I say things like the twin prime conjecture, there's only one set of integer. So I cannot really average over all the set of integer. But here, every time I have an elliptic curve, I have a conjecture. So I can say, well, look at the conjecture for all the elliptic curve. So sorry. And I'm going to average, okay, I have to choose one of the conjecture that I wrote. So let me take this one, the Elliptic conjecture. So, and of course, if you want to average, you're going to have for AB big enough. And actually, that's not trivial. What's going to be the, you know, the best AB big enough that you can have? Meaning, of course, you want it to be as small as possible. You want your average to be as small as possible. But it has to be, you know, if A and B are fixed number, then if you can compute that, you can compute the conjecture. So A, B are big enough with respect to x, huh? So what does it mean is A and B are bigger than some function of x. Well, typically the same one. So if you can do that, well, it's not going to prove that the conjecture is true for one curve, but it's going to be, we can prove that it's true on average. So for example, if I take the Elliptic conjecture, you would get that on average this is true, and you would get some constant Ct. So for t equal to 0, this is due to Fouvre-Murty. And if you take general t belong to z, Francesco Papalardi and myself generalized that. Okay, so this is one way to get evidence for those conjecture. So for the Elliptic conjecture, well, you get exactly square root of x over log x. It gives evidence, and just I'll just finish that. And you get a constant Ct, which of course does not depend on E, but your constant Ct is exactly what is the constant that was predicted by the conjecture, while removing weird factor which have to be there. Nathan is going to explain that in details. And not only that, you can also show that the average of the predicted constant is this constant. This is also due to Nathan. So it gives a lot of evidence. Not only it gives this evidence, but this is very, very nice, because this, of course, does not come in any way from saying, okay, I have probability of each prime and they should be independent and I have an Euler product. This comes from averaging over FP and the number match up. Yes? Oh, they're all, you mean non-zero? Well, I should have mentioned that probably in some cases. Well, for example here, of course, if the curve has rational torsion, certainly it is 0. But if you divide by the rational torsion, if the curve has the 2 torsion point, the number of points is divisible by 2 all the time. So it can be prime, but it doesn't happen often. So if you remove those things, for example, here you should do the divisibility, you can say when they're supposed to be 0 or not. Okay? And I'm sure Nathan is going to mention that. Okay, so this is those average result. And I should mention, yeah, the name of some people, as I put my name without any shame. So for this one, So, which is actually, so when Nathan is going to talk about that, I'm going to explain how to get upper bound for this one and this one. This one is much more tricky because you have to apply the Shibboleth in a tricky extension, which is the direct, not really the direct product, but some restricted product of two extension. So even to do the average here is very tricky. So this was done recently by Nathan, Elena Kujukaru, and Ivanic for this case. So for this case, I mentioned that it was done. For this case, it was done also by, so for this one, when you do the average, it becomes an average of the twin prime conjecture over the prime difference. Number of primes such that P and P plus R is prime is true on average over R, over the prime difference. So this is one of the tools that comes that you can prove that in average. It was done by Antel Balog, Elena Kujukaru, and myself. This one, done in average, Jim is thinking about that. He can prove that on average he has an upper bound of the correct order of magnitude, and maybe he has it, I don't know. You know, but he's working to, and this is kind of a mix of this one and this one. It becomes very complicated. So, and this is for the average result, yeah. So for those ones and those ones, there's reason that, you know, the tools are missing for the average result, which are related to what I will say after that. Okay, so I won't mention this at all. I think one of the nice features is this constant thing, but Nathan will mention it. What I want to mention is upper bound. Okay, of course, upper bounds are really not as satisfying as lower bound. This also happened for the twin prime problem. The first work, very well-known work on that, was the work of Bruns, who showed an upper bound. You know, you're going to say, come on, you want to show there are infinitely many twin prime and you're showing an upper bound? Well, this is, getting a non-trivial upper bound is not that trivial. For example, I don't know how to get a non-trivial upper bound in this case, you know, because there's no Shibboleth, and also in those cases. But there are some cases where it could be done. And this is what I want to explain, and the reason is that this is the Shibboleth density theorem. Okay, I'm going to start with the Lang-Trotter conjecture. So in fact, I'm going to obtain, this is what I want to do in the rest of this talk, I'm going to obtain upper bound for that, for this one, which is the number of, using the Shibboleth density theorem. Okay, why will I obtain upper bound? Because I'm going to do that. I think everybody would agree that this is an upper bound. So if AP is T, AP is congruent to T mod L. Okay? And this is what I want to detect. I want to detect AP is congruent to T mod L. We were able to detect P is congruent to A mod L. Can we detect AP is congruent to T mod L? So can we detect by using the Shibboleth density theorem in some extension. So if you remember, by using this extension, we could detect P is congruent to A mod L. Because P is congruent to A mod L meant the Frobenius would send zeta P to the A. So now I want to have an extension that will allow me to detect AP is congruent to T mod L. Well, it will also allow me to detect P is congruent to A mod L at the same time. Because, in fact, maybe my extension will be like that. So it will also detect me P is congruent to A mod L. So it will detect the whole characteristic polynomial of the Frobenius, because it detects the AP and the P. So how do I build those extensions? Well, this was mentioned by several people. So what time should I stop? Sorry. Okay, 25. So what are those extensions? I'm going to look at Q, and I'm going to join all ℓ-torsion. So this is the field obtained from Q. So this is the field obtained from Q by joining all the ℓ-torsion. Okay? This is the field that I want to look at. And remember that EL is so, and also that the Galois group of Q bar over Q acts on EL. So how does it act? If I have a point P, well, my point P is X and Y, sigma acts on all of those. Why does it act on EL? Because my curve is defined over Q. Huh? So it's important that the curve is defined over Q. Then if I do L P sigma, well, this is the same as L P sigma, which is back 0. Okay. My curve is defined over Q, so multiplication by L is just a big equation with the A and the B inside it, so it commutes with any Galois automorphism. Okay. So I have this structure. I have that the Galois group acts on that, and of course, it acts on that. Of course, it's an automorphism because I have the inverse Galois automorphism. So what do I get? Is I get a representation from the Galois group of Q bar over Q inside the automorphism of EL, but maybe I can fix a basis, and this is going to be like that. So fixing a basis. So what are the automorphism of ZL cross ZL? This is GL2. So this is just by letting, I'm not hiding anything. This is very simple. I'm just letting the Galois group act. And what do I do? Well, every time I have an element sigma, this is going to be sent to a matrix A, B, C, D, obtained by fixing a basis. So sigma of P is going to be AP plus CQ, and sigma of Q is going to be BP plus DQ. So I have that. So it gives me already some information about the Galois group. So maybe I can quotient by the kernel. I mean, this is a bit too big. So quotienting by the kernel. So quotienting by the kernel. Well, what is the kernel? Of course, it's the Galois group of Q bar over QEL. So if something fixes QEL, it fixes EL. By definition, we get. So you get an injection. This injects into. So, and now I want to do the Chebotarev density theorem. I didn't tell you that yet, but you know, looking at this will detect AP and P mod L. Well, I have to know how big is my group. If you remember, the Galois group is in the denominator. So an upper bound on the Galois group is not good. You need, you know, the exact size of a lower bound. So I want to know how big is that. And this is a big theorem due to Serre. So, and again, my curves are always non-CM, even if I don't write it. So rho L, or maybe I should say the Galois group of rho L is surjective for all but finitely many L. Well, and the finitely many L depends on the curve E. But given a curve E, well, forget about those finitely many L, rho L is surjective. So what do I get is that then, so the Galois group of QEL, I'm sorry, over Q is isomorphic to GL2 of all but finitely many L. Okay, what could happen for that the Galois group will not be that? Well, you can think about ℓ-torsion. You know, there are many, ℓ-torsion of elliptic curve, they correspond to the root, elliptic curve is y squared equals a cubic. The ℓ-torsion point is when the cubic f of x has rational point, rational root. This can certainly happen. Huh? I can write x minus 1, x minus 2. That would be my elliptic curve. And the full torsion group is defined over Q. So if the full ℓ-torsion group is defined over Q, the Galois group is trivial. Okay? So it could happen that those Galois group would be trivial, but this is only about ℓ-torsion. ℓ-torsion is very simple. I cannot do that all the time. And in fact, maybe I could have mentioned something before Serre's theorem. There's a theorem due to veil. Okay. I told you, well, you could have elliptic curve that the full ℓ-torsion is defined over Q. Just take your cubic to have 3 rational root. This can happen only for 2. It says that if EL, so this goes the same direction as Serre's theorem, saying this Galois group is big or this extension is big. EL is contained into K. This implies that the Lth root of unity, sorry, I should say EK, huh? The Lth root of unity belong to K. So if I have a field K, I have an elliptic curve over K. So if the ℓ-torsion is contained in my field, it means the Lth root of unity are in my field. So if K is equal to Q, this can only happen for L is equal to 2. And another thing I could say is that this result, Serre's theorem, it's a very nice result and not easy at all to prove, but in a way that's what you believe, because the field that you obtain by adjoining all the torsion points, this is just the splitting field of those enormous polynomial of degree L squared minus 1. And in general, though it's not easy to prove, a random polynomial has Galois group as big as possible. Okay, this is what is happening. If you take a random polynomial over Q, the Galois group should be Sn, yeah. Yeah, E has never. No CM curve never, yeah. Yeah, everything would be false. I don't want to write it all the time. Yeah. So, okay, the curve has no CM. Who looks about a CM curve, huh? You know, nobody wants to look about them, you know. Okay, from my point of view, they're not what I want. So I have this field, which is the field that you get adjoining the L torsion point. And inside that, I have the cyclotomic field by Veil's theorem. And now I have Q and this Galois group. I'm always going to pick my prime so that this Galois group is like that. Okay, that's my situation. And maybe the last thing I'm going to say, you know, so I see that I'm not going to finish this whole thing in 1 hour, so I'll go in the next one. So maybe the last thing I should say is that, okay, why is it related in any way with the Chebotarev density theorem? And this is because, is it good if I write here, do you see? Or this one better? Kif, okay. So this is a theorem that if I look at the map, so let sigma p, which belong to the Galois group of be the Frobenius at P, that Peter defined. Then, if I look at rho L of sigma p, okay, and I'm fixing a basis. I want to look at rho L of sigma p as a matrix in the GL2Z over LZ, is a matrix such that. So what's happening with this matrix, the trace of rho L of sigma p, well, is a matrix. Is a conjugacy class of matrix? Because I'm taking the prime down, so if you take the prime up, you get it's a conjugacy class of matrix. I can talk about the trace of a conjugacy class. It's invariant under conjugation, so I'm not saying nonsense yet. This is like that, and the determinant. Well, this one you would recognize as the cyclotomic character. Something has to be the cyclotomic character somewhere because the cyclotomic extension is contained. So when you take the Frobenius at P. And you look, what is the Frobenius? Okay, I'm saying rho L of the Frobenius. I could say the Frobenius in this Galois group. It's customary to use the language of Galois representation, but I could just say, where is the Frobenius at P is sent? So you saw that for cyclotomic field, the Frobenius at P was sent to the map which sent zeta L to zeta L to the A. So here it's sent to, well, when P is congruent to A mod L. So the Frobenius at P is sent to a matrix such that the trace is AP and the determinant is P. So that allows you to detect what we want. And I wanted to say about that. So 2 things is that first of all, so remark. So there are many conjugacy classes which have that. Okay. So and the Frobenius at P, in fact, we can write explicitly. I'm not going to use that. We can write explicitly rho L of sigma p, well, the conjugacy class, in terms of AP and BP. Okay? So if you want to pin down the exact element, you need the AP and you also need the BP. And what is the proof of that? Well, the proof is that the Frobenius is the Frobenius. We're over FP, so there are Frobenius everywhere. The proof of that is, as we said, that, you know, so the characteristic polynomial of, so phi p, this is the Frobenius on my curve. This is this map which sends xy to xy, x to the p, y to the p. Well, this is the Frobenius. This is what we want. Is so this is acting on TL. I should have said this is acting on the Tate module. So the characteristic polynomial of the Frobenius when it acts on the Tate module is exactly that. So it has trace AP and determinant P. You know, the characteristic polynomial of this 2 by 2 matrix. So this is at the Tate module. So this is at the L to the n limit. This is why you don't have any congruence. But if you see it acting only on the L torsion point, you will have a congruence mod L. On the L square torsion point, you would have a congruence mod L square. And at the limit on the Tate module, you don't have congruence at all. But for me, I need this congruence to get my result. Okay. So that's the main point. So I guess I'll continue next time. So I wanted to say application of the Shibboleth. Now we have everything to apply the Shibboleth. We have a question. We have a setting where the Shibboleth will allow us to answer our question. And now we just have to put all that together and look a bit at those questions. But I'll continue next time.